Please come.
Yeah. वो सामने रखा है क्या? Oh, this is that Himachal. Welcome. Welcome. You can keep these things in the bag.
Hello. Yeah, okay. Thanks to Professor Bera for inviting me for this talk, and thanks to Professor Aditya for introducing. So as you know, in this talk I'll be dealing with non-coherent communications for CMOS systems. And before I start with the presentation, where is the keyboard? Yeah, okay. I will just go through some key events in India on communications, okay? So I thought I'll just go through it first. So, this is just a chronology of certain main events on communication technology in the country. So first in 1882 we had the opening of the first telephone exchange during the British rule. And then 1895, J.C. Bose, he demonstrated the first wireless transmission over short distance, okay? Using the Mercury coherer, and so this happened in Calcutta. And then 1902 the first wireless telegraph station was established. I don't know exactly where, somewhere in the country. 1927 the radio telegraph system was demonstrated by Marconi between UK and India. Sorry, this was not Marconi, sorry. 1927, this was between UK and India, the telegraph, and then radio telephone system inaugurated between UK and India in 1933. And the first Marconi's demonstration, I don't remember the year, but it was done after 1895. He demonstrated between England and Signal Hill in Newfoundland in Canada over the Atlantic. That was for longer distance. But the first wireless transmission was demonstrated by J.C. Bose. Then first digital microwave junction introduced in 76, and 79 first optical fiber system commissioned at Pune. Then first satellite earth station for domestic communications established at Secunderabad. That time it was Andhra Pradesh, now it is Telangana. Okay, then 84, this is the government policy towards the IT sector changed, and when Rajiv Gandhi became Prime Minister, and then CDOT was established, okay, Center for Development of Telematics. It was established by Sam Pitroda, and the first, CDOT made the main change. Many of you have not seen those days. That telephone connections used to be really bad, and it was difficult to get through lines. And later these STD booths came up, okay, and it continued for quite some time. And this STD booth concept, it happened after the CDOT revolution. And of course now it has faded away with the advent of mobile phones and the proliferation. So 1995 the first mobile telephone service was started by Bharti Airtel on 15th August 1995 in Delhi. And I think the cost that time was 8 rupees per pulse, something like that. I don't remember the exact cost. Yeah. So now today the Indian telecom market is one of the fastest growing in the world, and it's the second largest network in terms of wireless subscribers after China. Then they are no more a status symbol, as you know, and India is among also the 3 countries that have built supercomputers on their own. And India is among 6 countries that launch satellites and do so even for Germany and Belgium. And INSAT is one of the world's largest domestic satellite communication systems. And of course, TCS, Infosys, they are world renowned for their IT prowess. This is still, this was updated few years back, so now there are more things, and I will need to update it further. So this is, I thought I'll just give a snapshot of certain main events. Okay, so back to the main talk. So this is a joint work with Professor Ross Murch of HKUST and Soumya Das, who was my PhD student, and he is a faculty in IIT Bhubaneswar. Saif Mohammed is my colleague in IIT Delhi, and Jack Winters, he used to be in AT&T many years back, and he has his own company in New Jersey. So this is the outline. So first I'll introduce the topic, then the system model, then the error analysis for the maximum likelihood receiver, and then optimization of signal amplitude levels for the ML receiver. Yes? No, it's fine. Absolutely fine. So,
should we just
no, I'll use the. Is this working?
yeah, that is
Okay.
working. Caller mic
Okay,
has-
then I'll take the color mic. Okay. Then I can move around.
Yes,
Okay, fine.
I'll just turn it on.
Then
Yeah.
that other. Yeah, thanks. So we'll put it here, right? On the other side.
Other way.
No, I think this is the right way. Possibly.
Whichever way it will work.
It should work both ways.
Yeah,
Maybe this.
yeah, this is the right way.
Okay. Hello. It's kind of.
You can put it in the neck as well.
कैसे?
Just like this.
I normally, yeah, those clip wala hota hai. Okay, this is fine. Okay, thanks. This is cool. Okay, so then what happened to this? Is it working?
Yeah, it is working, but it is very small.
Okay, fine, got it. Okay. So then the error analysis for the modified, we basically consider non-coherent receiver but with two variations. So one is the modified maximum likelihood and the usual maximum likelihood, and then the optimization of the levels for the modified ML receiver, and then some numerical results and the conclusion. Okay, so as you know that low power and low complexity receivers are needed in a variety of applications, like wireless sensor network, short range interconnects, and cooperative communications, emerging technologies such as 5G, and non-coherent communication can offer reduction in complexity, power consumption, and signaling requirements. So basically no requirement for pilots for channel estimation, so the general overheads are much less if you have non-coherent detection. And so investigation on the performance of non-coherent systems is now becoming relevant, especially with the advent of sensor networks and ad hoc networks, where you cannot afford high power consumption. Now, there are two important configurations with respect to multiple antennas. One is DAS, so distributed antenna systems. These are spatially separated antennas but connected to a common transceiver system. And the uplink channel gains to each of the antenna elements are differently distributed due to large separation between uplink antennas. And so the correlation between the antennas is low or nil. The other one is massive MIMO, multiple input, multiple output. So you have multiple antennas, the transmitter and or the receiver, and hundreds of antennas in an array, and uplink channel gains to each of the antenna elements are often identically distributed, and the correlation between antennas is higher due to proximity. Okay, and so utilizing non-coherent communication allows a straightforward front haul instead of an optical fiber front haul, as required in non-coherent DAS and massive MIMO systems, and it also avoids channel estimation. And so now, as regards to modulation, generally for non-coherent systems you use FSK or ASK. You cannot use PSK, right, or its variants. So you cannot use QAM, for example. So FSK or ASK, they both have their advantage and disadvantage. FSK needs high bandwidth. ASK requires very little bandwidth, but performance-wise, FSK has better performance, but at the expense of bandwidth. So there's nothing like this is bad, this is better always, and this is bad always. It's nothing like that. Like situation dependent. The performances and the advantage and disadvantage are situation dependent. So the focus of this work is on non-coherent multi-level ASK. modulation with receive diversity combining in a daily fading environment. So we will not consider transmit diversity here. Okay, just a single symbol transmission, and you have multiple antennas at the receiver. Now we consider different cases of the channel covariance matrix. One is uncorrelated identical fading, okay, which is basically IID fading. Then you have uncorrelated fading with distinct mean squared channel gains. This is uncorrelated non-identical fading. It covers DAS example. And the other is exponentially and uniformly correlated channels with equal mean squared channel gains, okay. It covers massive MIMO. And we consider two types of receivers. One is the maximum likelihood receiver, this is the optimum receiver. It's a quadratic combining receiver. And then the modified maximum likelihood receiver, which is suboptimum. It's a deterministic linear combining receiver. Now, there is some previous work on multi-level ASK. One is there's some work on ASK for AWGN and log normal channels, and then there is optimization of signal levels for UWB IEEE 802.15.3a channels. Okay, and so here what we do is we derive closed form expressions for the symbol error probability using the statistics of the decision variable, and we also find the optimum signal amplitude levels that minimize the SEP subject to a total energy constraint, and then of course some results from the numerical optimization. All right, so we consider single input multiple output environment, and sorry. Yeah, so basically this is the received signal vector, n by 1, there are n receive antennas, and this H is the channel vector, okay, it's complex in general. We are considering Rayleigh fading, so it will be either way correlated or independent, so it's basically zero mean Gaussian vector, and times S, which is the symbol, which is an ASK symbol, so it will just be, and because it's non-coherent detection, it has to be one-sided ASK, so you cannot have plus minus 1, plus minus 3, etc., like you have for coherent ASK. So it will have 0, 1, 2, 3, that kind of levels, and plus this additive noise. Okay. So we are considering multi-level ASK signaling, L levels, and a priori probabilities are equal, and non-coherent reception. So let's look at the receiver structure. So the signal constellation is you have L levels. So if E1 is the signal energy EI for the ith level, so the levels are root of EI, I equal to 1 to L, and average symbol energy is just summation of EI over L. And of course, they without loss of generality, you can assume them to be in ascending order. Okay, and so it's Rayleigh fading, and you have a covariance matrix of KH. Mean is 0, the vector H, and n is of course the noise vector, and sigma n squared is the variance of the noise, and I is the identity matrix, which is n by n. They are independent of the channel coefficients. So we consider 4 cases of the channel covariance matrix. One is uncorrelated identical fading, that is KH is scale version of identity. Okay. The next one is you have uncorrelated non-identical fading, in which the diagonals of the covariance matrix are unequal. Okay. But of course, we are taking the sum is equal to n, capital N, which is the number of receive antennas. And the other one is the exponentially correlated channel with equal mean squared channel gain. So basically, it will be what we call an exponential correlation matrix. So it's a Toeplitz matrix. So the off diagonal element between the I and the jth, which is at the ith column and ith row and jth column, is epsilon to the power of mod of I minus j, right? So epsilon will go from -1 to 1, and the diagonals are sigma h squared, and the off diagonals are sigma h squared times epsilon to the power of mod of I minus j. Okay, and then the other one is the uniformly correlated channel, in which the diagonals, off diagonals are all equal, epsilon. Now the range of epsilon in this case is -1 over n minus 1 to 1. It is because it has to be positive definite, right? So you cannot be -1 to 1 arbitrarily. It will tend to see, when n is large, it will gradually tend to 0. It will become 0 to 1. But otherwise, for a 2 by, it is only for a 2 by 2 matrix you will have minus 1 to 1. That's it. For the rest, for example, for 4 by 4 you will have minus 1/3 to 1 the range. Now, in all the cases, one thing is clear, that sigma h squared is trace of kh by n. Okay, right? And so suppose lambda 1 to lambda n are the eigenvalues of the normalized channel covariance matrix, which is kh by sigma h squared. So in case of uncorrelated non-identical fading and exponential correlation, these are all distinct. Okay. For uniform correlation, you will have one eigenvalue which occurs only once, which is 1 plus n minus 1 into epsilon, and the others will be repeated n minus 1 times. So these are standard results for symmetric matrices. And then what we can do is we can always do an eigen decomposition of kh. So you can put it as sigma h squared into u times lambda times u Hermitian. So u is the vector of is the matrix of orthonormal eigenvectors, and lambda is the diagonal matrix of eigenvalues. Okay. And for uncorrelated non-identical fading, that is IID case, you just have u equal to I, right? Now the average SNR per branch of the ith symbol is EI sigma h squared by sigma n squared, and the average SNR is summation of sigma I over L, gamma I over L. And decision rule, this is the receiver decision rule. You can easily get it by just taking, you have to just take the maximum likelihood receiver, that is the distribution of R given S. You have to average over the statistics of H. So if you do that, you will end up with this kind of receiver. So you have to find the maximum over all the symbols of, see, you have R Hermitian times some matrix times R plus a bias term. So this is basically a quadratic receiver, right? Now, this is the optimum receiver. Now, you can also have another kind of receiver in which you do deterministic combining with a weight vector G. So what you do is you combine the elements of R with you just do a linear combination with the elements of G. With a, normally because we are dealing with complex quantities, we use the Hermitian instead of transpose. That's okay. It doesn't matter. You could take it as G transpose also. It doesn't matter. But I've just taken it as Hermitian. So it's sigma of di conjugate times Ri, right? So that you take the likelihood function of that. Okay. So that gives you this receiver. So here what happens is this is whether the dependence of R comes here, okay, and G you have to find out, work out what is the best G, and that we'll see later. And there is again a bias term which depends on G here. So G is deterministic; it's not random. So R of course is random because what you receive is dependent on the fading. So right, and of course on the additive noise. So G is chosen such that it minimizes SCP. That we'll see later how it is done. Okay, now let's look at the error analysis for the maximum likelihood receiver, the optimum receiver. So what you do is here the standard. This is basically related to quadratic forms of Gaussian variables. Okay, and what you can do is you take the main decision variable, which is this one, okay, and you assume some signal is transmitted. You can assume the ith signal is transmitted. So I have taken lth signal. I have taken the ith signal is transmitted, and you are matching it with L, the lth signal. So if there is a perfect match, I will be equal to L. Otherwise, if it is not, it's an imperfect match. So you find out you just evaluate the same decision variable. the same quadratic form and then take its statistics. So what happens is this will be a gamma distribution, or rather a gamma type distribution, not exactly a gamma distribution. So this is what the characteristic function will look like. This is the characteristic function of the decision variable. This is the decision variable corresponding to the Lth signal given the Ith signal is transmitted. Okay, and this is its characteristic function. So you'll have this, and these BKIs are given like this. BKL is EL times sigma h squared times lambda k. We have seen the eigenvalues of kh plus sigma n squared. Okay, and they will go in ascending order because the way we have chosen the energies. And we have also, we choose the lambdas such that they are in ascending order, so there is no problem. You can always, take the eigenvalues in that order. So this is the characteristic function, and then we can express that like this, and these are as a linear combination of exponential variables. Okay, and then finally this is the probability of correct decision. So you have this plus the bias term is greater than this plus a bias term for L not equal to I, for L equal to 1 to L. Okay. So you can find this by, so now another thing is we define the quantity CKL as BKL plus 1 by BKL, which is essentially this. Gamma L plus 1 times lambda k plus 1 divided by gamma L lambda k plus 1. These gammas are dependent on the E's, right? The levels, the ASK levels. So they'll just be in increasing order. So there's not a problem. All CKLs are greater than 1 by default, by definition itself. Okay. So what we can do is we can express the probability of correct decision in this form in terms of the C's in front of the X's, and we know the statistics of X because we know its characteristic function, right? And then we can simplify it. This is a bit intricate. So what happens is that this can be shown that these quantities for all for all 1 to I minus 1 are maximized when it is I minus 1, and these are all minimized when it is I plus 1. So what happens, you basically compare the current symbol with only the previous one and the next one. That is what the long and short of it is. So not previous in time, I mean previous in index. Okay. So this is the probability of correct decision given ith symbol is transmitted. So then you can simplify it further, and you can get the probability of error. Okay, the symbol error probability from that. It is basically this, right? 1 minus. Yeah. So if you simplify this, you will get this, and then so now let us look at, so what our objective is to find out what this part is, right? These terms are, what the values are, or whether you can get any expression for them, that we can. So we have to look into because you know the statistics of these X's, right? It's not a problem. And so first case is the very simple case. It's the case of uncorrelated identical fading. So what happens is all the lambdas are 1. Right? The U is identity matrix. So this is the case of IID fading, and then CKI will not be dependent on K anymore. It will just be CI, right? So so the probability of error will be given like this. It can be easily shown. So this function G of UCIN is this. Okay, it can be easily shown. So it will be a function 1 plus function of CI and then a minus function of CI inverse. Okay, and all the CIs are greater than 1, as I have said before. And of course, it can be shown that this monotonically decreases the increase in each of these. So what does it mean? It means that if you make those CIs as large as possible, then you will get a better performance. So, and what are those CIs? They are basically SNR plus 1 divided by SNR plus 1. So what you want is, you want the symbols, if you have suppose 4 symbols or 8 symbols, you want them to be far apart between each other as possible. So I mean, it does not make sense make one distance very large and then the rest are clustered. It does not help because there are so many symbols. So that's the main thing. So what is the best way to space the symbols? Because the standard method for coherent ASK is that you just take the levels in arithmetic progression. Basically, the voltage levels are taken in arithmetic progression, so the energies become square of arithmetic progression. But that is not the best in this case, because that is for coherent reduction. Okay, so now, first of all, we have not ruled out the possibility that the first level could be 0. We have not said that. So we have taken it is between 0 and I mean some positive value, all the levels, but the first level could be 0. We have not excluded that from the beginning. So here now, first of all, you want C1 to be as large as possible, obviously, because it is monotonically decreasing increase in each of these CIs. So at least make C1 as large as possible. What is the best way to making it as large as possible? You just put E1 equal to 0. That's the best thing to do. You can do for any arbitrary E2, right? So you first choose the first level as 0. This is the reason you choose it. You want the probability of error to be as low as possible. Okay, so that is one of the things for the IID case. Now the other one is when you have these lambdas are not equal. This is uncorrelated non-identical fading and exponential correlation cases. They are both similar. Why? Because what happens is when you have exponential correlation, all the eigenvalues will be distinct. That can be shown. I don't want to get into all that. But for uniform correlation, you have one distinct eigenvalue and the rest of the n minus 1 are repeated. But in exponential correlation, all the eigenvalues are distinct. So it is they are the same cases. It doesn't matter because ultimately it is the eigenvalues which matter, not the eigenvectors, at least for these cases. So in this case, so now in the case of exponential correlation, for n equal to 2, 3, 4 closed form expressions for the eigenvalues can be obtained. And for n greater than equal to 5, it is difficult to obtain such closed form expressions. I have a paper on exponential correlation matrix which appeared in 2018 in Transactional Wireless Communication. So that has the details of this kind of matrix. Okay, so anyway, the bottom line is that they merge into a single case, the non-identical independent fading and the exponentially correlated fading. So now here what you do is you define the function h like this, and these vi's are unit mean exponentially distributed random variables. Okay, and so this function can be expressed like this, and the only reason is to we form a similar function like we formed this function g, right? For this case, for the IID case, we'll form a similar function in this case also. So here the function g becomes can be expressed in terms of h. So and then we can express the probability of error the same way, just like before. Just the function is different. Again, in this case, of course, you have C1i to Cni and then like that. It is not C1 to Cn like before. I mean, it's not it's not just Ci. You have multivariate function. Earlier it was a univariate function, right? For the IID case. So this again, it can be shown that minus of this function monotonically decreases increase in each of the C1i to Cni. And so again you choose the first level as 0 by the same logic as before. Okay, now the uniform correlation case. Now this is slightly different because you have one eigenvalue which is repeated n minus 1 times and the other is fixed, repeated only once. So in this case again all the C's will merge into one and you have one Cn. And here you can define a similar function h, and then you can again have another g in terms of h, and this is how this will look like, the probability of error. Yeah, similar way, but you have only two, it's a bivariate function now. You don't have so many values like the exponential case. Okay. So again, by the same logic, you choose the first level as 0. So the bottom line is you choose the first level as 0. You start with 0 level, and when L equal to 2 levels only, you have on-off keying. That's the simplest case. Okay. Now next will be we can certainly optimize the signal levels for best performance. There is no optimization for 2 levels because the first one is 0 and the second one is twice the average. That's all. But for 4, 8, etc., you can always optimize. And so the optimization problem is like this, that we minimize the probability of error subject to the energies, such that the sum of the energies are equal to some fixed value, and they are all in ascending order, and the first energy is greater than or equal to 0. Okay. So in this case, what happens is that you can get the EIs in terms of the gamma, capital gamma is, all those things don't matter. So you can reduce it to, in terms of optimization, in terms of gamma 1 you can take as 0. So you just reduce one variable. So for uncorrelated identical fading, which is basically IID case again, you can do the optimization, and I'll skip the steps. You can do it partially analytically, and so finally what happens is you get the for large SNR, okay, when the SNR is high, what happens is the levels are in geometric progression, not in AP, they are in GP, okay, and the GP ratio can be obtained in terms of this gamma average. Okay, so yeah, so basically this is the main result, that why doesn't this the first okay, so this is the main result. So these E1 is 0, we know that. So root of E2 to root of EL, they are in geometric progression with common ratio this. Okay, and so the optimal signal amplitude levels are approximately in geometric progression. Okay, E2 onward, E1 is 0. So the asymptotic SCP expression is like this, and the diversity gain which you get is actually n over L minus 1. Okay, which is not that great, but this is the best you can do. It is after all non-coherent detection, right? So you cannot get results like coherent detection. So if L is 2, the diversity gain is n, as expected for received diversity. But in this case, it is n by L minus 1. Okay. Now for uncorrelated non-identical fading and exponential correlation, same case. So you can define this function capital G like this, and the optimization problem can be simplified. And so when you do the optimization, well, this is optimization problem, okay, in terms of the this function capital G, and then these are the optimization conditions. You can only solve it numerically, can't do anything better than that. And for uniform correlation, the problem is similar, but the optimization function is different. See, the main difference is the number of variables in the function G. So here you can see there are n variables. In this one, because of repeated eigenvalues, you just land up with 2 variables. Okay, and so yeah, you can solve it numerically like before. And now for some asymptotic results, okay, that is high SNR. We have already got the asymptotic result for IID case. Now for the correlated cases, for the uncorrelated non-identical case, and for the others, what happens is you get similar result as before, that just that the GP ratio, the common ratio, which is this one, it has the lambdas here, because IID case the lambdas are all 1, right? So here it depends on the lambdas also. So you have the same thing, that they are all in geometric progression asymptotically, and they are a function of the eigenvalues of the normalized covariance matrix of the channel, and the number of receive antennas, and number of levels, ASK levels, and of course the average SNR per branch, which is gamma average. And of course sigma n and sigma h, the variances of the channel and the noise, additive noise. Okay, So again, the diversity order is n plus n by L minus 1, no change. But there is an error performance degradation in case of the other, apart from IID case, it's lambda 1 to lambda n by minus 1 over L minus 1 as compared to the uncorrelated identical fading case. Okay, so it will degrade further. Okay, and this is an example. If you have a massive MIMO system having n equal to, I mean, we call it MIMO, but it's actually massive SIMO. It's n equal to say 105 and epsilon 0.1 with exponentially correlated fading and L equal to 4. It gives probability of error of 2.4 into 10 to the minus 16 at 20 dB and a diversity order of 35. The error performance degrades by a factor of 1.4 compared to IID case. So this is just measured. You can take lower values and get a higher probability of error and less degradation. Now, if you have high average SNR and high mean squared channel gain estimation, channel gain imbalance or high correlation, that is basically the what you call the condition number between the eigenvalues, right? So what happens is, say 1 out of lambda 1 to lambda n, say lambda n is approximately n and the other n minus 1 approximately 0. So if there is a huge imbalance, and then what will happen is you will have the same thing, just these parameters. You will again have the GP approximately in geometric progression, but you will have a common ratio which is different. It will depend only on n, gamma average and L. That's all. This is an extreme case. And the diversity order will be 1 over L minus 1 in this case. Strangely, there is no n, right? Now this, for example, if you have a massive MIMO system having 100 n equal to 105 uniformly correlated fading with high correlation and L equal to 4, then you will have 3.9 10 to the minus 3 as the P, which is much higher than before at 20 dB and a diversity order of 1/3, which is not really a good performance. Uniform fading is an extreme case, you know. It does not occur all the time. Okay. Now, so far we have done with the optimum receiver. Now let's look at the other receiver, which is the modified ML. Okay. And here, this again the same method. You have this DLI, which is the when ith symbol is transmitted and you want to see the division variable corresponding to the lth match, and then you find out the G Hermitian times R. You want to find its statistics. From that you get these quantities B again as before, just that each B will be a function of G. Okay, and so we can express the DLI like this, and the probability of correct decision, this looks simpler, but we let G Hermitian G equal to 1, and in this case the quantity CL looks like this. Okay, it's yeah, it has a dependence on G. So the question is, how do you choose G, right? So you get similar kind of expression, and you have the same yeah. So this is what the probability of error will look like. Okay, and this GUCI1, this is basically dependent. It is just like the same what we had for IID fading with N antennas. You just put N equal to 1. That's all. That is the main difference. And of course, your CIs will depend on G. Now, what is G? Now, P monotonically decreases, increase in each of the CIs, right? So what you want is each of the CIs you want to be as high as possible, right? So first of all, you choose the first level as 0, and what you do is you choose G equal to the eigenvector corresponding to the maximum eigenvalue of the normalized covariance matrix. That's what you do. That will give you the best performance, and therefore your sorry, this will be C1 and this will be CL for L equal to 2 to L minus 1. Okay, because gamma 1 is 0, your C1 is just this. So it will depend on the covariance matrix, of course. what the maximum eigenvalue is. This is for uncorrelated identical fitting, lambda max is 1, because you know, there is no maximum eigenvalue as such. I mean, all the eigenvalues are equal to 1. And for uniformly correlated channel, what happens is, depending on the value of epsilon, the eigenvalue will be, what will be the highest eigenvalue. So if epsilon is negative, then what happens is 1 minus epsilon will be larger. And if epsilon is positive, then 1 plus n minus 1 epsilon is larger. So depending on that, you choose the eigenvector. So the eigenvector for when epsilon is positive, which is in this case, it is all ones. Okay, normalize it by root n. And if epsilon is negative in this range, then it is any vector orthogonal to all ones. So one of the vectors is this. You have n minus 1 vectors which are orthogonal to all ones, right? It is like if you have x1 plus x2 plus up to xn equal to 0, it's a plane, right? It's an n minus 1 dimensional plane, and any vector on that would be perpendicular to all ones, right? It's basically that. You can choose orthonormal, but it's a n-dimensional plane of eigenvectors, n minus 1 dimension. Okay. Now for this modified ML receiver, you can do the same kind of optimization, and you will end up with again the same geometric progression. Okay, asymptotically, no difference. In this case, the diversity gain is 1 over L minus 1. Now, some of the numerical results. So one is L is the number of amplitude levels, just to remind you of the notations, and N is the number of diversity branches, and gamma average is the SNR per symbol per branch. This is the channel gain ratio, and this is the correlation coefficient. Okay. So now uncorrelated identical fading and the ML receiver. So these are the highlights. The performance of optimal signal amplitude levels is better than that with levels in arithmetic progression, obviously, and in the arithmetic progression case, the SCP is close to that in the optimal case for low SNRs, but the performance gap increases with increase in SNR. And when the levels are in arithmetic progression, the SCP tends to reach saturation, which is not desirable at all when gamma average becomes large. I mean, you can avoid the saturation, it's best. Always you can't. Sometimes when you do multiplexing, you do have saturation in noncoherent case. You cannot do anything about it. That is with multiple transmit antennas also. Okay, so this is a performance of 4-level ASK with varying n for uncorrelated identical fading. You see the curves which go to saturation, they are the ones with arithmetic progression, and these are the ones with optimum levels. You know, they have a waterfall kind of. With the diversity gain will be n by L minus 1. That we have already seen, right? Then these are some values of the CIs for this for the ML receiver with IID case. So, you know, if you have L equal to 4, so there will be 3 CIs, right? And this is gamma I opt. So if you see the optimal SCP and you the SCP with gamma I plus 1 in geometric progression, you will find that the relative error is very little. So basically, if you do not want to do the optimization, you just take the levels in geometric progression. Actually, what you need to do is, because of course the first level will be 0, the other levels you just put 1 plus gamma equal to r to the power of I minus 1, where where r is the common ratio of gamma I plus 1. So obviously, if you have I equal to 1, you will automatically have r, gamma 1 equal to 0, right? It's automatic. There's no need to bother about anything. And so this is a quick way of calculating the levels. You just put 1 plus SNR in geometric progression. Okay, and this is another example. That one was with n equal to 8. This is with n equal to, I'm sorry. Yeah, that's okay. This with L equal to 4. This is N equal to 16. So better performance, of course. You can see the SEPs. Of course, you see, this is you should remember one thing, that this is non-coherent detection. So don't get alarmed by the values which are relatively high compared to coherent or differential detection. So you see, it's 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. It does not look very nice, but this is the SEPs. You see, but this is the best you can do. This one is better, as you can see. Like 10 to the minus 4 you are getting here, this is 16. So if you increase the number of receiver antennas, you will get better performance, no doubt about it. And for this is for if you have uncorrelated non-identical fading with ML receiver, the performance degrades with increase in the ratio of the eigenvalues. That is the channel gain imbalance for a given n, and the performance gap with respect to n reduces with increase in channel gain imbalance. Okay, and for exponential and uniform correlation and ML receiver, the performance degrades with increase in correlation for a given n, and performance gap with respect to n reduces with increase in correlation. And it also results in an increase in imbalance among the eigenvalues, increase in correlation, which is expected, right? And these are values of, again, optimum levels for an optimal SCPs of 4 level ASK with n equal to 8, and gamma average 12 dB and ML receiver. This is just a comparison with the, see, you have the various cases, okay. See, uncorrelated identical, this is IID case, uncorrelated, this is uncorrelated, exponential case, uniform case, okay. These are the SEPs, so you can compare and see. This is of course the best. And then, this is okay and this is not too good, because the condition number is increased. And then here again, exponential 0.9 is too high correlation, so that's why the performance is also lousy. This is better. Uniform 0.7 is okay, but this is not good, 0.9. And between uniform and exponential, you can see that the exponential 0.7 is this, uniform 0.7 is slightly higher. Okay. Of course, if you increase n, you will get better performance. So the basic pattern is known. This is n equal to 16, better performances, same kind of thing. Okay, these are some plots of the same kind of things. So this is SEP versus channel gain ratio. Those lambda k1 plus lambda k. Okay, so you can see that. So the cases are of. This is for arithmetic progression. This is optimal. So these black and red curves are arithmetic progression cases. Arithmetic, geometric and optimal. So you see optimal and geometric will be very close, the red and the blue. They will be closer. This is the arithmetic progression case. This is the geometric and this is this thing. For n equal to 8, 32 and 64. So 64 of course gives the best performance, right? It is increasing with increase in the condition number. Now this is for exponential correlation with 4 level ASK and ML receiver. See, the previous one was for uncorrelated. This is for IID fading. No, uncorrelated fading with unequal eigenvalues, right? This is for exponentially correlated fading with 4 level ASK. So here again the increase is there between the black, the red and the blue. So the blue gives the best performance, optimal, which is close to geometric progression, and then the arithmetic progression case is slightly away, and this with respect to epsilon. That's the correlation. This for exponential correlation. You can have a similar one for uniform correlation. This is again for 10 dB, this is also for 10 dB. This is for uniform correlation. Similar, but worse performance. You can see that if you compare with this. Trend is the same. Okay, and this is for varying in and channel gain ratio. This is for uncorrelated fading and ML receiver. This is with optimal levels and with varying in. This is with optimal levels. That's why you have the waterfall kind of thing. And it's just seeing the channel gain ratio, So channel gain ratio equal to 4 gives the worst performance, equal to 1 gives the best performance. Channel gain ratio 1 means all eigenvalues are equal, right? Okay, and this is with this is for uncorrelated fading, and this is for exponentially correlated fading. Pattern is the same, and this with uniformly correlated fading. Okay. So now for the modified ML receiver, these are some of the trends. The performance, so far we saw the optimum receiver. The performance improves with increase in lambda max, and increase in channel gain imbalance for uncorrelated non-identical fading, increase in correlation for a given n for exponential and uniform correlation, and lambda max is approximately n for uncorrelated fading with high channel gain imbalance. Okay. So the main thing is the trend here is reversed, because if you have a greater channel gain imbalance, you have a better performance in this case, which you do not have in the case of optimum receiver. Here it's slightly different because you're using a deterministic vector to combine the received vector. Okay, so this is this for optimal with optimal levels. Okay, for this modified receiver with the vector G. So you can see that these are the 4 cases of the correlation, and the of course this is for n equal to 40, 420 and 800. So I purposely, I mean, this just to get some reasonable performance. Here of course to get a reasonable performance, this 10 to minus 3 almost, you know, you are going up to n equal to 800. It's pretty high. It is not always a wise thing to do this, but this just an example. If you do that, this is what you will get. And this is for on-off keying. Okay, with the modified ML receiver. There is no optimization here. On-off keying is just straightforward. Okay, so this is the conclusion, that we have investigated non-coherent detection for multi-level ASK, and so we have considered 2 types of receivers and 4 types of presence of correlation or lack of correlation. So one is IID case, one is unequal eigenvalues independent, the third is exponential correlation, fourth is uniform correlation. 4 cases and 2 kinds of receivers. And so with increase in imbalance among the eigenvalues of the channel covariance matrix, the error performance degrades for the ML receiver, improves for the modified ML receiver. That's the main difference. And the optimal ASK constellation for minimizing the SCP subject to a total energy constraint is not uniformly spaced. It follows an approximate GP spacing at high SNRs. So these 2 are the main findings actually. One is this one and one is these 2. Right. Okay, so these are the references from which these things have been taken. First was the first paper deals with the CMO IID case. This appeared in TCOM in 2014, and the second one is with correlated uniform and exponential correlated case. A similar kind of situation, and the third one deals with deterministic combining. Okay, they are all from identity transaction communications. Yeah, and so I'll also show you the first pages of 2 other papers, which are not exactly related to this, but I think they are important for MIMO and for Rayleigh fading. They are my own papers, and they are both single authored. I'll just show you. Okay, this is one paper on MIMO which does not have the word MIMO in it. You can search and see. Okay, so this is 2003 April. This is called Analysis of Transmit Receive Diversity in Rayleigh Fading. So it considers the concept of maximal ratio transmission, and it considers PSK. Okay, and so what you do is here this is the main signal model. Okay. So this is the weighting vector, and this is the symbol. Okay. So you have a weighting vector here because you are using multiple receive antennas, right, and single symbol. So you are not multiplexing here. Okay. So you are using actually transmit diversity. So it considers IID relief fading, simple case. So this is one, and it has the expression for the probability of error in terms of these ultimately gamma type distribution related summation, and yeah. So this is one. It basically uses the result of the maximum eigenvalue of H Hermitian H when H has all its elements as IID Gaussian. So that is what it uses. Yeah. So this it finds out the statistics of this for getting the performance. Uses the concept of Wishart distribution. So this is one, and the other one is this. This is for this IEEE transaction information theory, June 2003, a few months after this. So this is on multivariate Rayleigh and exponential distributions. Okay. So this basically considers the general case of Rayleigh fading, in which you have correlation between the in phase and the quadrature phase also. But crisscross. See, in Rayleigh fading for a single channel, for every channel, the in phase and quadrature phase have to be independent. That otherwise it's not Rayleigh. But you could have correlation between one channel and the other, the in phase of one and the in phase of the other, in phase of one and the quadrature of the other. It's possible. So that it considers the general case. So that's the other one. Okay. So that's all I had to say. This is also the first single author full paper in the history of independent India, which appeared in IEEE Translation University. It's a shame. It is nothing to be proud of. Since independence, people have been not doing much. That is what is the thing. So there is one short paper which appeared by somebody from Indian Statistical Institute years before that. That's all. You can check in ISI Web of Science. So this was the first full paper. Because earlier information theory used to have both short and full papers. Nowadays they don't. They have only full papers. So after I published it, I checked. So I found this is the only first paper. So they appeared only in 2003. Independence we got in 1947, right? So it's a shame. Nothing to be proud of. I'm glad that people are more active these days in research, which is good. So okay. That's all I had to say. Thank you for your patience. So questions are welcome. Or maybe I should keep it on. Yes, please.
So good afternoon, Professor. So I have questions related to those optimization problems you have.
Yes.
So you mentioned that they are done numerically.
Yes.
So is there any guarantee given that these are solved optimally, or these they are local optimas or something?
That I do not look at, but these are actually simple optimization. It's not a very complicated one. Simple constraint, You just have a linear constraint and the function is nonlinear, but it's not a non-convex, etc. case.
But then you have a lot of strict inequality constraints. I'm not sure how did you handle them in.
What I did was, you can get a semi-analytical solution. Like if you start with the IID case and the other solutions are following the same trend. So you can get a semi-analytical solution. So when you actually do the optimization numerically using some standard package, for high SNR they match with the semi-analytical solutions. But I have not made this kind of verification as you asked.
Okay.
But my understanding is that I don't think it is a problem with there is any issue with local versus global here. I don't think so.
Okay.
Because the asymptotic ones match, na? So that's why. I have not, but somebody could look into those details. Okay. Possible, yeah.
So I have another question related to that modified ML receive.
Yes.
So essentially you are doing something receive beamforming, right?
Correct.
So
receive combining actually.
Receive combining.
Right.
So receive combining requires some understanding of the channel.
It requires understanding of channel statistics, not channel, not not CSI.
Not CSI, but this
Statistics you need, yeah.
Statistics you need.
I have another paper with Jack Winters on deterministic combination, but that is for non-coherent case. I mean, that's for non-coherent case. But yeah, it is basically receive combining with deterministic weights. That is the main thing, but you need knowledge of channel statistics. So you avoid the channel estimation. See, all this is basically to avoid overheads, nothing else. We are doing all this exercise for what? Just to avoid overheads.
True.
And power consumption, the receiver, that's all.
Yeah. So
Yeah.
now I have just this concern that, see, if your goal is to minimize probability of error,
Yes.
so should it not be that the one of the optimization variable should be that G? That
It-
G.
It is related to that.
But then you are assuming that it is already that optimal receive beamforming, like with respect to that.
Oh, you are taking, no, I did optimize G.
But so it's supposed to be simultaneously optimized.
Okay, yeah, no, I did not do that. I did in 2 steps. Yeah, you are right. Yeah, you can do simultaneously. I did not try it that way, but it is possible. You are right. Yes, I understand what you are saying.
Yeah. So will that be different from what you have obtained, or it is already understood that this is what optimal is?
Did not look into it, frankly.
Oh,
And nobody questioned this.
Okay.
But I'm glad you are questioning it. And if you want to pursue it yourself, you are welcome to. This was done some years back, and see, reviewers nobody asked this question.
Yeah, I agree.
So if they had asked, possibly I would have looked into it.
Okay.
But yeah, it is possible to jointly optimize. Definitely, yes. This is just a shortcut, you can say.
Uh-huh.
You first maximize it, and uske upar
Yes,
you do
yes,
it. Yes,
even I do that actually. That
yes.
alternate optimization.
Yes,
and all.
yes.
So, one
But
last
then the complexity would increase. Maybe you'll
Yes.
get the same result, may not be. We don't know.
yeah.
May not be also. But it needs to be looked into.
So I have this concern related to why did you only consider that positive values? Is it because
Which positive?
So this signal levels, they are all positive.
Oh, this is because is non-coherent ना वो plus minus काम नहीं करेगा.
Oh, is it?
No. Plus minus काम नहीं करता.
And then if
That's a well-known thing. वो phase inversion हो जाने से काम नहीं करेगा.
But then accordingly, like when we calculate that expected SNR or something, there the underlying assumption is that your signal, that expected signal value is supposed to be 0, right? That happens only when you have.
No. Not for non-coherent. See, non-coherent में only things which work are FSK and ASK, or combining of these two. Actually, I have another paper more recent, which it is not yet. It is accepted. It is there in the early access. It is on something which I have found out, that is combination of FSK and ASK.
Okay.
That is also possible in non-coherent case. So it will appear in transaction wireless communications. I have not got the volume number here, but there in early access. It's also a single author paper.
Okay.
Yeah. So that has that. But apart from FSK and ASK, I don't know of any other method of keying which will work for non-coherent.
Okay.
I don't. What else? I mean, phase, frequency, amplitude. What else will you do?
Yeah, true.
See, QAM is a combination of amplitude and phase. I have worked on FPK also in another paper. So that's you combine the frequency, you use the information of the frequency as well as the phase together. You can do it. So that is also possible, and but that is for coherent detection.
So lately those antenna-based modulation schemes which are coming,
Those you mean spatial ones?
special one.
हाँ,
Can
तो those are all variations.
Okay.
वो तो antenna based तो is like intensity modulation actually.
Okay.
In some sense, yes.
So can they be also put in this framework?
It can be put in the same framework. Yes, it can be, of course.
So I have one last question.
Yes,
this
please.
is related to so high SNR assumptions.
Yes.
Is it valid for a sensor network?
Well, to some extent, it depends on what the SNR is. If it is like maybe 15 dB up to, it's okay. It is obviously not 30 dB in general. Yeah, depends on your hardware.
Okay.
But yeah, as I say, even diversity gain, is it the best measure? No. It only if the diversity gain occurs in a reasonable range of SNR, it makes sense. If it is occurring at 100 dB, what use is the diversity gain? Useless.
Yeah, true.
That's the thing. So some people are obsessed with diversity gain. So they need to understand it in the right spirit. that it is sometimes useless. BER is always, BER or SEP is always useful. Again, capacity is another, it's an asymptotic measure, you know. People misuse capacity like hell. Because they don't know what else to do.
True.
And then outage probability का जैसे करते हैं ना, for everything they are using outage probability because they don't know what else to do. Find the SNR and then उसका statistics लेके outage निकाल लो. Because modulation के साथ करना is more difficult, ना?
True.
So, you know, finding diversity gain with respect to outage is ridiculous sometimes. But people do it. It is wrong. And first of all, diversity gain itself is questionable in many situations. So people don't understand these things sometimes. They just say diversity, tending to infinity means infinity is just a concept, right?
Agree.
So if it is 15 dB, it is okay. If it is 30 dB, it is not okay.
Yes, true.
Not for the kind of networks we are, or the situations we are thinking of.
Yes.
Right.
Okay.
So,
Thank you, Professor.
okay, sure.
Sir, yeah, this is more not of a question but a request, which
tell
is because I see there is a diversity of this audience from BTech and some PG students as well.
Yeah.
So the 4 cases that you have discussed being for the channel which is being correlated, uncorrelated and exponentially correlated,
Yeah.
and along with uncorrelated with different values. Fine.
Right.
So it will be easier for the students to grasp it if you can give some example scenarios where actually these are happening. That will help the students to
See, for
actually understand it,
uniform correlation, it is mostly if you have either large MIMO cases or when you have closely packed antennas. That is one situation. Exponential correlation is, well, it is difficult to give a specific scenario offhand, but if the spacing is like not too little, it works. Sometimes they are not exact. See, exponential correlation is not, they either use uniform correlation or sometimes some correlation from readings.
readings. Yeah.
Yes, which have arbitrary eigenvalues. So, exponential correlation is not always used, but because it's a Toeplitz matrix that has certain properties which are helpful, they often use it because it can be used in approximation for something else. So, you can see there is a concept of distance between matrices. Na? So, correlation matrix mein you assume one correlation matrix for the other, which is the reality and the approximate. If it is not, distance is not too much, chalta hai. At least some things will work. I mean, some values will be okay. It's like that. Yeah.
Just one more thing, which is as Siddhartha pointed out about the optimization problem.
Yes.
And I believe I see the current trend which is going towards from doing the optimization at 1 or 2 variables with which is coming from going from matrices based optimization to tensor based or multidimensional optimization, and I believe that would be the direction.
Yeah, that
in
of
which
course.
it will go
I have
and
not, I mean, I have
it
not
can be
taken too
solved.
many cases of too many variables anyway. Because see, the number of antennas is, you can take more, but levels to ASK mein bahut zyada levels karoge, performance will be rubbish.
Rubbish, yeah. For at least for non-coherent.
Beyond 16 levels, it makes no sense.
And one more could be that we can exploit the code as well.
Kya?
The code as well. As in-
Coding you mean?
Yeah, yeah.
This is raw data. So
this
you
is
can
raw
use
data,
coding.
yeah.
Yes, yes.
You can use coding and then can be able to, you said ASK and this the other one, and then we can use a little bit of coding as well, and then we can.
Yeah, that way,
do
coded
data.
modulation.
Yeah.
Yeah, that would be another thing. Yeah.
Okay, that's all I have.
Okay, thank you.
Thanks, yeah.
Anyone? Okay, so with this, I would like to thank Professor Ranjan Mallik
My
for
pleasure.
sparing time. And this was really, talk in which we have seen it's a very focused content that he has tried to give you. And you must have seen that the vast amount of work that he has done and the highly impactful work, the way in which he has said. So I'm sure that our faculty members, those who are working in the area of communication as well as the students who are working must be very,
So
happy and got motivated.
all the PDF files are here, so you can share it.
Yeah, thank you.
So,
Yeah, in communication. Yeah.
yes, I know. I think it was one, the audience who are present is not too many, so in that way it is better.
Yes, it is good that today is a exam time. Otherwise, many would have been disappointed. Actually, you people have to tell the speaker. so little.
Yeah.
Then he would have come prepared.
Yes, yes,
Ah,
of course.
so he came highly technically. You didn't have any question? Huh? Okay. So probably you should invite him with a much more, educative.
I
See,
can give a more
normally,
general talk, of course.
I told him today, I told him that why don't you speak how communications, progress 1G, 2G, 3G, 4G, 5G, 6G, and why India is saying is 6G is our product, right? Because at his level, he can easily present these things much better. Yeah, more educative. Okay, thank you.
Thank you, sir. Thank you very much.
Thank you. My pleasure.